Hello, everyone. Thank you so much for joining the webinar on this lovely afternoon. We're switching up our normal time frame today, and we're just so excited that you're here to join us today. Our webinar will be 30 minutes along with time at the end for Q&A. During the webinar, you can send your questions through the chat icon, which is located at the bottom of your screen, and we will answer your questions during the Q&A portion at the end of the webinar. We will be issuing PDH certificates for those attending the live session today that have elected to receive them. A copy of the presentation will also be included post-webinar. All of our webinars are available on demand at bartlettwest.com, and we will continue to add webinars, so please refer to our website for upcoming opportunities. Today, we will hear from Brian Hainline. Brian has 33 years of experience and 27 years at Bartlett and West. He has a wealth of expertise in water treatment and distribution, design, facilities planning, construction administration, water rate structures, and project funding. Today, he will be discussing ceramic membranes and the potential advantages. With that, I'm going to turn it over to Brian to start our presentation today.
Thanks, Rebecca. Can you hear me?
Yes, I sure can.
Okay, thank you. Just want to make sure. And welcome everybody this afternoon. I'm assuming most of you at least have some basic understanding of membranes, but let's see, you get going. Okay, so gonna run through some basic membranes information for those of you that might be a little bit newer to the membrane environment, and then turn our attention specifically to ceramic membranes, which are starting to become at least they're entering the US market and becoming more of a viable alternative. And then kind of wrap up with one example case study that I'm aware of, and we'll go through some cost information and advantages that they specifically observed. So, so where, again, where within the treatment process are membranes utilized? Here's an example of a groundwater plant, or maybe a groundwater under the influence of surface water plant. And in this particular, schematic, the microfiltration, ultrafiltration membranes, which is what we're talking about today, they might sit up at the beginning of the process ahead of RO, possibly in that application. Or if you have more of a conventional surface water, a river, a lake, you might have a myriad of different sorts of preliminary pre-treatment type things happening. But at some point, you're going to come to the filtering step, and your choices are media filters or MF or UF filters. So that's where, within the treatment process where these membranes would apply. Within the membrane world, there are kind of two main categories. There's microfiltration, ultrafiltration, which I've already mentioned, and that's what we're visiting about today. Historically, here for the last 20 years in the U.S., polymeric has been the material of choice. And as I mentioned, the ceramic is now starting to enter this arena. And then we get into nanofiltration and reverse osmosis and EDR, which were also membrane processes, but they have a completely different function and do serve a different purpose than what we're talking about today. Again, just a quick recap. MFUF, they are primarily particle removal applications. That's what they do. They take out turbidity, bacteria, giardia, crypto, oxidized irons and metals and arsenic and any sort of metals, things that are in a particle size that are where the particles are larger than the pore size. What they do not remove is dissolved minerals. Dissolved manganese goes through MFUF all the time. Viruses are very small, and for the most part, they'll go through these membranes. Color, if you got some sort of pesticides, herbicides in your source water, they're going to go through. And total organic carbon, or probably more specifically dissolved organic carbon, will go through these membranes. I'm going to touch on NF and RO just a little bit here, just to kind of part of this recap, and then we're going to set those aside for the rest of the day. Nanofiltration, which I tend to think of as sort of a loose RO or a low pressure RO. We started getting into water softening, disinfection, byproduct precursor removal. We'll start picking up viruses. will start picking up even dissolved metals and sulfate, and depending on how tight the membrane is, you're going to pick up some nitrate, which is common in groundwaters. When you go up to an actual reverse osmosis membrane, you're pretty much going to take everything out of the water. It's almost just strictly H2O at the end in the permeate. Some terminology you're going to hear me refer to a lot today, and again, most of you are probably already familiar with these terms, but the feed water, that's the water that's going into the beginning of the membrane equipment. The permeate or the filtrate is the produced water that's coming out of that membrane system and that's moving on to the next step in the treatment process. The transmembrane pressure is the differential in pressure between the inlet pressure and the outlet pressure. And I'm going to get into this more, but there's, in most of these membrane systems are pressure driven. So you're pumping the water, you're pushing the water through the membranes, and there's that differential pressure. We call it TMP in the membrane world. Flux is another way of talking about a loading rate. Those of you that are familiar with media filters, you size media filters based on gallons per minute per square foot of surface area. Membranes or MFUF membranes are sized in terms of gallons per day per square foot of membrane area. So that's where the you might hear me refer to GFD or flux throughout this conversation. Fouling happens on all membranes, and it's accumulation of the particle matter, uh, coagulants that you might be using, anything that's in that water that's being filtered out. Most of it can just be backwashed off, but some of it eventually kind of, fouls the membrane to the point where that transmembrane pressure reaches a point where you've got to do a clean. And there's a few different cleaning steps, but you'll hear me talk about CIP or clean in place. That's a process where the actual skid is taken offline, usually for several hours, and you might do a high pH, you might do a low pH, you might do both in back-to-back sequences, but often you create this solution, you put it into the membranes, you let it set, you recirculate it, and the high pHs tend to take organics off, and low pHs are going to take off metals and things like that. You might also hear people talk about a chemically enhanced backwash. Typical backwashes on these are just water only, and they happen every 15 minutes to 45 minutes. But maybe once a day, you'll do a chemically enhanced backwash where you add a little bit of chlorine or maybe a little acid, just to kind of, it prolongs the time between the CIPs. One last thing on NFRO, and then we're going to put that aside for the day. So again, most of you are probably familiar with what an RO skid looks like. The modules, they're spiral bound. It's a sheet with some inner layers, and it's wound. And the feed water to an RO has to be very, very clean. So that's why oftentimes MF or UF might be used as a pre-treatment to an RO system. And they're usually housed in these long horizontal tubes with 5 to 7 modules stacked up end to end inside of those skids. So just a couple of pictures of what an RO skid might look like. But again, that's not what we're talking about today. So as we get into the actual membranes themselves, so again, MFU of polymeric membranes, I became aware in the late 90s, early 2000s. That's when they started to enter the U.S. market. And now they're widely utilized, and they run a combination of the dirty waters on the outside, clean waters on the inside, or the other way around. It's very, basically I refer to this as kind of angel hair spaghetti. That's what you can think about this as, much smaller than that. But all these fibers are then bound into modules. This module here is a pressurized one. This module here is for a submerged application. And the membrane itself is actually either this thin inner layer or outer layer, depending on which mode of operation it's in. And the rest of this is just a structure to kind of give it some rigidity that kind of forms the straw, so to speak. A couple pictures of what pressurized systems look like. Again, in this case, each one of these vessels is a module. So there's one module in each one of these vessels, and they're typically mounted vertically, as is shown in these pictures. And the one end of the skid's typically got all the valves. There might be feed pumps. There could be pre-filters. There could be a wide range of things that's happening on the end, depending on the application in the plant. But they all tend to look somewhat the same. Submerged membranes is the other style that's out there. Pretty heavily used in larger sized plants. This happens to be pictures from Mid Dakota Rural Water in central South Dakota, and it's a plant that Bartlett and West did. And again, you can see the submerged membranes in that case. So moving on now into getting into the beginnings of the ceramic membrane conversation here today. This technology is being led from Germany and Japan. And I guess I want to preference the rest of this too. You're going to hear me talk about certain manufacturers the rest of today. I'm not promoting them. They just happen to be the ones I'm the most familiar with, have the most information on their particular equipment. But by no means is this a sales pitch for any one manufacturer. As I've mentioned earlier, ceramics are becoming a player in the domestic market in the U.S. They're available in both tubular form, and I've got some pictures of that coming up, or flat sheet. We're going to talk about both of those in the coming slides. One of their advantages, they have a higher flux rate. I'm going to get into some numbers coming up, but that flux rate is oftentimes 2 to 4 times. So if you had a polymeric module that was doing 25 GFD, that ceramic might be doing 100 gallons per day per square foot types of an environment there. So the point is you end up with less modules than you would with polymeric to produce an equivalent amount of water. One of the things that ceramics, another advantage is they have less temperature effect in cold water. And for those of us that are up in the Dakotas and in the northern parts of the U.S., where the water can get down to just barely above freezing, you can have a wide change in the capacity of your plant between a warm water condition and a cold water condition. So that water temperature becomes very important to us. They have higher chemical resistance, so you can be like a little bit more aggressive with your cleanings or maybe your backwash approach, because they're not going to break. One of the things that happens with fibers is they break, and you spend quite a bit of time, or the operators spend quite a bit of time, periodically, might be once a week, might be once a month, but they got to go and take those modules off and repair them, so to speak. When in repairing them, you're not fixing it. You're actually just, you pin both ends. You're basically blocking off the broken fiber so it could no longer function. You put it back into service again, which I guess gets into higher mechanical strength. So you don't get into that breakage. Ceramics are coming out with, at least the ones I'm seeing, 20-year warranty periods. At least currently, the current polymeric ones, at least the ones I'm aware of, are typically around 10 years. So you get double that warranty period. So if a polymeric lasts for 10 years, you're going to go through 2 sets of those modules by the time you would have gotten through 1 set of the ceramics. So the ceramic systems are probably not going to be your least upfront capital cost, but I think you will see them become the financial better choice if you look at life cycle cost over the course of 20 years or 30 years of time, taking into account that module replacement cost. And I've got some information coming up later on maybe less cleaning frequencies or less chemicals required. So some cost savings and just longer life. So this was a chart. We're working with Mid Dakota Rural Water and looking at maybe some expansions of their plant. And so they have a plant that's rated 13.5 MGD at 60 degrees Fahrenheit, and that's a flux of, in this particular case, 42 GFD. But in the wintertime, when their water is 35 degrees Fahrenheit, that equivalent amount of membranes has kind of an allowed rate of about 8.6. So that's quite the change there, a decrease in capacity. And in their particular case, I've kind of got this highlighted here. So their peak demands hit in May, June, and July, when livestock calving and birthing is happening, crops are going in, heavy farming operations. But you'll see this line. So the water temperature is still going up. And so this becomes the point in the year when the operator gets the most nervous that he's nearing his plant capacity. And when they get up to 60 degrees Fahrenheit water, well, they're in September, and the water and the demands are start going down. So again, this is a unique case. It's on the Missouri River with the large lakes, and there's a big lag time throughout the year on the water temperature. If I went and showed you the same thing and say a smaller lake in Kansas, this graph is going to look different. But anyway, you can see the effect that temperature has on polymerics. I also spent a little bit of time talking to an experienced membrane design engineer, again, trying to further continue to understand the temperature impact on these membranes. And again, he gave me some information. If we're looking at pressure style polymerics, 35 GFD if it's 15 degrees C, 25 GFD if it's 2 degrees C, and then likewise Nanocells happens to be a particular manufacturer. But you can see, even I guess he's suggesting that there might be some temperature effect, depending, I suppose, on how conservatively you design your plant. But you can notice that the large difference between the flux rates between a polymeric and a ceramic. And then going into submerged style, again, similar numbers on the polymeric. And again, Serafiltech is another manufacturer. They all these membranes have a coating on them, and what those coatings are made out of plays some part in the flux rates. But again, you can see the significant jump between polymerics and ceramics in those applications. So again, these are just general numbers. You may very well find that temperature doesn't have as much of a dramatic effect on your specific case. That's the key about all these, any membrane plant or any water treatment plant in general. Everything is unique, and just because your neighbor's doing something 20 miles upriver, so to speak, doesn't necessarily mean that same thing is going to apply in your situation. Again, this really applies to kind of all membranes in general, but the ceramics are starting to get into it. And so there's two key certifications that they need to get to have in possession to really become players in the U.S. market. And one is the NSF 61 certification. And for those of you that are in the water industry, you know what that means, but that's, this equipment, it could be pipes, it could be valves, it could be the membranes in this particular case, but you have to take that equipment, you give it to NSF, they run it through a series of tests, and they're confirming that there are not things in that material that are going to come out into the water and contaminate the water, in your drinking water plant. And then the other one is NSF 419, which is a challenge testing protocol. And this used to be kind of done out in California by the California Department of Health. Now it's kind of migrated to the NSF. So if that manufacturer says, here's this membrane, and I've got these two certifications, you're pretty much know that they're good to go in the US, because those are the key ones that they need to have in hand. And the ceramic ones, they're starting to apply, at least the two that I'm familiar with. I believe they both have their NSF 61 certifications, and they're both starting to work on their NSF 419 certifications. Again, all membranes, but again, we're talking about ceramics here. Almost all UF membranes, in particular NMF, or you'll get your 3-log Giardia removal credit. You'll get your 2-log crypto credit. And in some states, in some unique cases, you might get some virus credit. I typically don't assume I'm going to. I just assume I'm going to have to get my 4-log virus inactivation through disinfection. So again, in general, how do these ceramics work? So you've got this kind of this outer structure, and they make this structure. They run it through a kiln and heat it and harden it, and then they apply the actual membrane coating itself and run that through and heat it also. And so you've got this inner thin film that's actually the membrane. The outer part's just to hold it together. And then as it's working and particle matter is being collected, that cake also can help further become a filtering system. And again, all membranes work like this, but the ceramics in particular. Getting into some types of ceramic membranes. So we've got multi-channel, and there's a whole list of manufacturers here. I'm not aware of any of them being in the U.S. market in a municipal drinking water application. But these are like little tiny tubes, and you you bundle those together to kind of make that module. So similar to the way the polymerics are, it's just that you're not going to have as many of them. And again, you can see the holes. And again, the clean water is either on the inside or outside, depending on how that particular manufacturer set theirs up to work. Then there are other manufacturers, and Metal Water is one of the manufacturers that actually has a couple of systems in place in the U.S. And so they kind of create their module in one big monolithic creation, is how theirs is done. At least that's my understanding. And then you're going to hear me talk quite a bit about nanostone throughout the rest of the conversation. And again, that's just because they're kind of active in South Dakota. They got some plants in South Dakota, and I'm familiar with them. In fact, we're getting ready to do a pilot study with some of their stuff at Mid Dakota here, frankly, in about a week. But I'll get into more about them. But they're a pretty major player, at least from my perspective, particularly in the upper parts of the United States. And again, in part because it's a ceramic and they've got less cold water impact. As I was mentioning, again, this is my understanding of things. I very well could be incorrect, but Colorado's and Montana have one ceramic system each, both manufactured by Metal Water. Nanostone's got 3 in South Dakota. Well, 2 that are actually in service in South Dakota, 1 that's under design, 1 in North Dakota, and 2 in Texas. And again, if somebody's on the call and says I'm incorrect, that wouldn't surprise me. Serafiltech and Safbon I-10 are the 2 flat sheet manufacturers that at least I have some knowledge of that are looking to get into the U.S. market. They don't have all their certifications yet, and so they're as I've said, almost all this market's coming from Germany and Japan, and so there are certainly systems in the world that are in the domestic water market from all these manufacturers and probably others, but relative to the United States, these are the players, at least as I know them today. Talking a little bit more about Nanostone here, so again, here's their module. Again, their module is really made up. These are actually flat sheets. So they took flat sheets, come up with a way to form them. They have potting material on the outside, and they run inside out. And so the dirty water goes down these inner pores, and the water comes out these. I should back up here just a second. So the water's going in these pores and coming out in this slot in between, and then exiting out the side ports. So the feed water comes in the bottom. The waste goes out the top, and the waste on these systems is no different than the waste from a media filter. It's going to go to some sort of on-site backwash recovery basin. It might go to on-site lagoons. It could go into the sanitary sewer system if you're inside of a community. So the waste, again, all you're doing is collecting the same material you would have collected on a media filter, and you just got to deal with that waste in the same manner. I guess Nanostone's actually got 3 layers. They've got the outer, kind of that outer support structure. They've got an intermediate layer, and then they have the actual membrane coating itself, which is on the inside. Ceramics, they're hydrophilic, which means they're water loving, and that's part of the reason for their ability to have the higher flux rates, which I've mentioned several times. And again, the ceramic it's kind of like having a rock. I mean, it's kind of hard, so they won't fail. You aren't going to have fiber breaks with the ceramic membrane. You might have potting material failures. You might have O-ring failures that would cause you to not meet your daily integrity tests that have to be performed on these systems, but you're not going to have the fiber repairs. And I'm sure if you talk to any operator that's got a polymeric membrane system, they will explain to you how many man hours they spend on a weekly or monthly basis dealing with broken fibers. In some cases, it can be quite significant. This is some information on one of Nanostone systems. This is one of their systems in Texas, so a much larger plant, 10 MGD. But again, you can see the 130 GFD in the summer versus 45 polymeric. And in that case, again, this is Texas is not getting as cold, but again, they had the same rate in the wintertime, and 25 GFD for the polymeric. And to get the equivalent amount of capacity, you'd have to actually have 3 more polymeric skids than you would with the ceramics to get an equivalent amount of water under the various water conditions. So if you start thinking about that in terms of cost, the membrane module themselves may be more expensive. But if I have to have an extra skid or 2 extra skids, all of a sudden that cost starts to catch up quite a bit. So going forward, I think Bartlett West, anytime we're writing reports and we're talking about MF or UF systems, we'll have a part of that report that's going to discuss polymeric membranes, and then a part of that report that's going to talk ceramic membranes. And we'll talk to vendors, and we'll get preliminary budget costs, and we'll have some information in that initial report that compares the two. And then from that point, what happens will be on a case by case basis. But we're going to start putting this into a lot of the things that we look at going forward. Getting into the flat sheet side of things. So again, you've got the sheets that are kind of made in, it's a module. The modules go into a cassette. The cassette goes into a tower, and then you header together a few of these towers, and then that's lowered into your tank. I got another picture coming up here in a second. So this is kind of what the flat sheets will start to look like, at least in the drinking water applications. Now, there are, I think, flat sheets are already being used in the U.S. in some wastewater applications, membrane bioreactors. I believe there are, ceramic membranes already being used in that application, and that's not what I'm talking about today. But I do know that those are out there, and there are lots of manufacturers out there that make membrane systems and ceramic systems that are used in wastewater, fruit juice, other sorts of industrial applications. But it's not on the domestic water side, and I guess that's the focus of my discussion today. Again, just kind of outside infiltration in this particular case. So you've got the plate sitting in there, it's accumulating the particle matter, and then periodically, and these backwashes happen. Again, this is common to all the membrane systems. They all have to be backwashed, and it might be every 15 minutes. It may be every 45 minutes to an hour. It just depends on all the various factors: water temperature, loading rates, what you're loading it with, and what has to happen to keep that membrane clean. Another picture of kind of that same thing with the flat sheets, the modules, the towers. And again, these are submerged, so they're, you have a crane and you lift these towers into the tank. So just like that photo I showed you earlier on of Mid-Dakota's submerged membranes, you would take those out and put these basically in their place. And Sarah Filtech is actually making systems that are, their intent is to be able to replace the polymerics and fit something back in that same space. Safbon ITN, I know they originate from Germany, and this happens to be one of their applications in, I think this was someplace in the Middle East. So it was hot water. I think on the terms I've got a little bit over 100 degrees Fahrenheit type water. And if you look at the polymeric information, 47 GFD versus, somewhere between 200 and 250 GFD on the ceramic, and their backwash frequency is 45 minutes versus almost once or twice a day. And their cleaning, remember that I mentioned that chemically enhanced backwashing and the CIP stuff went from whatever frequent means, but I'm assuming that means every 2 weeks to every 4 weeks to maybe upwards of 3 months. And in this particular application, I think what was happening is the polymerics were actually failing because of that hot water temperature. And so the ceramics being a ceramic product, that temperature didn't affect them. So this was the plant that was retrofitted with some of their systems, but again, in the Middle East. Moving into kind of a little case study. Again, this isn't one that Bartlett West had anything to do with directly, but it happens to be in South Dakota, so I'm familiar with it. Or I've actually mentioned, talked to their operator a few times at conferences, and have toured this plant once or twice. On the left-hand side was the polymeric membranes that they had, and on the right-hand side was the ceramic membranes that over the course of a year or so they replaced. And I've got some information here shortly. This is out in Rapid City, so they got Rapid Creek, which is a very clean water supply, so they don't have to do a lot of pre-treatment. They add some coagulant, they add chlorine. It goes through their main membrane skids, UV disinfection and chlorine, and basically out to the system. They also have a backwash recovery system. So the backwash off of these skids goes into a backwash recovery tank. And they had a small backwash recovery polymeric skid, and that's really how this started for them. They were having a lot of problems with that secondary skid, so they used it as a pilot test essentially for the ceramics, and they performed very well for them. And that eventually led them into them changing out their two main skids. Some of the reasons that they looked at making these changes, again, they were fiber breaks. They were having a fair amount of those. Again, this is South Dakota in the surface waters, so the cold water impact. They've since found that they're saving, I've got some numbers coming up here in a bit, but they're saving quite a bit of money per year on chemical savings in terms of cleaning costs. And they were actually able to increase their capacity of their plant, but stay within the same footprint of everything they already had. So they didn't have to expand anything as far as footprint goes. So they had two primary skids. Each one had 50 polymeric membranes on it at about 1 mgd each at 38 GFD. And when they completely finished replacing those with the ceramics, so the same 50 spots with ceramics, so they gained a half mgd per skid, so they gained 1 mgd of capacity, even in cold water at 125 GFD. They went from the polymeric, they were having to do chemical cleans about every 600,000 gallons of production, and then went up to 3.5 million gallons. So a significant change there. There's no air scrub in this particular system, so their backwash downtime was about half, but we're talking about 30 seconds. But if that's happened fairly frequently throughout the course of the day, you're gonna gain a few more minutes of production time. And they estimate about $16,000 a year in savings in just chemical cleaning costs for their main system. I mentioned to you they had the secondary backwash system that was operated at 50 gallons per minute, and they went from 10 polymeric modules at 22 GFD to 4 ceramic modules at 69 GFD. And the polymeric, they were having to clean about every 18,000 gallons of produced, and that went up to 80,000 gallons. So again, a lot less frequency, and they're estimating they're going to gain back an additional $11,000 annually in chemical cleaning cost than that. So all told, they're looking at $27,000 of less chemical costs, and that will certainly help offset some of the cost of the ceramic modules. I think I'm nearing the end. Just a typical skid. So one of the projects that we're working on for design is Standing Rock Rural Water in northern South Dakota, and they have 3 existing polymeric skids, and we went through a procurement process, and we're going to put 2 nanostone ceramic skids in beside them. So sometime probably within the next year or so, we're actually going to be having 2 systems running side by side on the exact same water. We'll be able to gain a lot of information and data on comparing the 2 to each other. But again, for those of you that just, what is one of these skids, size wise, they're often somewhere between, 25 and 35 foot in length, anywhere from 6 to 8 foot in width, and usually around that 12 to 13 foot in height. And so this particular system here was rated for 1,000 gallons a minute production, net production. So in summary, again, some of the ceramic membranes, they are becoming a viable alternative, not in every application and not in every case. But I would urge you, if you're looking at getting into the membrane world or market, or looking at maybe changing from polymerics to something else, that the ceramics have gotten to a point where they are worth your time having somebody investigate those for you. I've mentioned several times the higher flux rates, less to no water temperature effect, no fiber breaks to have to repair, higher chemical resistance, longer warranty periods. As I just demonstrated in case of Rapid Valley, uh, less chemical cleaning frequency and less chemical cleaning cost. And again, it's a case by case basis whether on a life cycle basis ceramic would win, but they're probably not going to win just on straight upfront capital costs. So anyway, I believe that's the end of it is my last slide. So at this point, I will certainly entertain any questions.
Thank you, Brian. Yes, we're going to open it up for Q&A. So if you have questions, please send those through the chat icon. Again, you can find that at the lower portion of your screen. As we wait a couple moments for questions to come in, I do want to thank you again for sharing your time with us today. Thank you, Brian, for sharing your expertise with us. As a reminder, a recording will be available on our website at bartlettwest.com. I did want to ask if I have someone that joined via the telephone, it's area code 608 ending in 583. If you could in the chat, drop your last name, as we will be issuing PDH certificates based off attendance. I don't want to miss anyone, so I did see that. Thank you for joining in that way. We like to provide as many solutions or ways in which you can join, so I would greatly appreciate that. Checking here on the chat, Brian, I am not seeing anything. His contact information is included here, and we do encourage you to connect with him directly. At this point, if I don't see any further questions, we'll go on and wrap up our webinar today. Thanks again for joining us. We hope you have a fabulous rest of your day, and we hope to have you join us for a webinar in the near future. Thanks so much, everyone. Take care.